So Lian,
Good morning, sir.
uh, can, can you now start sharing the screen?
Yes, sir.
Right, so Dr. Lian Dasallas is also from UP Diliman. He's in the Material Science and Engineering program of the College of Science. So Dr. Dasallas, you can start.
Okay, good morning, everyone, and thank you, PAASE, for providing a venue to share our work. The title of my work or the presentation is Computational and Experimental Works in Post-Laser Ablation and Deposition, which is uh, basically the summary of the activities of our research group. Now, before I proceed, I'd like to thank my collaborators. First is Dr. Garcia, who is my dissertation advisor, and Dr. De Vero, who is my research supervisor. Previous collaborators include Ms. Lacaba and Mr. Patricio, who's now working in Maxim Integrated. And bulk of the work now is being carried out by our PhD students, Joseph, Jane, and Romil from NIP, and Jenny and Joy in the Material Science and Engineering program. Now, the work that we have been doing in our group is represented by these two simple part. First, we have the laser ablation, and the second part is focusing on the film deposition. So although these two processes looks like very simple, they are in fact rich in many, I would say, exciting physics when it comes to light matter interaction. Now, allow me to focus first on post-laser ablation. This is a technique wherein portion of the material is removed from the surface, and this removal from the surface is accompanied by the generation of a luminous plasma plume, which is uh, list shown in this figure. This is a useful technique in many areas such as surface patterning and in some chemical analysis part. Now, investigating pulse laser ablation is uh, a very active work now, and there has been many approaches to study it, especially when we use femtosecond pulse laser to provide the excitation. We have the molecular dynamics, hydrodynamics, rate equation, and two temperature model. These approaches can be applied depending on the material in consideration and the available computational resources. On our group, we focused first on metallic materials, and a very good approach to study ablation of metal is to use the two temperature model. And this model is written in this slide. Basically, what we have is a transfer of energy from the photon to electron to the lattice. This transfer of energy is described by these two coupled nonlinear partial differential equation. And we have C as our heat capacity, K as the conductivity, TE as our electron temperature, TL as our lattice temperature, and so on. The S in this equation is what we call the laser source term, and is useful and is typically given by this equation. As you can see, it is a function of the reflectivity and the laser fluence, along with the material properties such as the ballistic length and the penetration depth. Now, in most of the investigations done using the two temperature model, almost all of them assume that the laser pulse will approach the surface of the target at normal angle of incidence. But in some cases, the normal angle of incidence is not advisable. For example, in pulse laser deposition experiment, the substrate is located at the opposite part of the target, so you can't uh, put the laser path here. And on the other issue is what we call the plasma shielding effect. The laser is less effective when it passed through the laser produced plasma, and it will be more effective if it passed through the side. So what we did is to modify the existing two temperature model in cases where oblique angle of incidence is needed. So to do that, we just have to uh, place in the angle dependent reflectivity, which is given by Fresnel equation. And we modify the fluence and beam waste to take into consideration the changes in the beam waste. So basically, the laser source term will look like this. And along with the boundary conditions, we can now do the pulse laser ablation modeling. To do that, we need to incorporate the physical properties of the metal, such as the optical and thermal properties. So in our work, we focused on copper, which is described by the critical point model of the dielectric function. The relaxation time is given by this equation, and the conductivity is given by this equation. The heat capacity and the electron phonon coupling factor is given by this equation. But if we are to put this equation into our modeling, the computation time will be longer. So what we did is we performed the polynomial fitting to the already solved electron heat capacity and electron phonon coupling factor in order to improve the computation time. So this is the result of our work. Typically, what the two temperature model gives us is the temperature of the electron and the lattice as a function of distance and on time. Shown in the left is the electron temperature, and on the right is the lattice temperature. So basically, at time right after the laser pulse hits the copper surface, the electron readily heats up, and after a while, the lattice will also increase its temperature. Now, as we know, the reflectivity is dependent on the angle and on the polarization. So what we did is to modify the angle of incidence and the polarization of the incident light. And as you can see, the electron and the lattice temperature decreases with the angle of incidence. And we see that the polarization also dictates the overall temperature of the copper surface. Okay, in fact, when we use p-polarized light, we can obtain a higher temperature compared to s-polarized light. However, the electron lattice relaxation time remains constant at almost constant at a different angle of incidence. We plot the maximum temperature as a function of the angle of incidence, and we see that they follow different cosine power behavior. So the one with p-polarized light is shaped like this, but with s-polarized light is shaped like this. Okay, the fitting factors such as the amplitude and the power of the cosine is given in the table. Now, the I would say the experimentally verifiable output of the two temperature model is to determine the depth of the crater formed by the pulse laser ablation. So in this slide, we determine the depth at different angle of incidence and polarization. And we see that they follow two different regime. At low laser fluence, uh, the depth as a function of fluence follow a logarithmic behavior. However, at high laser fluence, they behave almost like a straight line. From our investigation, we have seen that the higher angle of his incidence will result to a shallower, meaning less deep ablation crater. And since the temperature is higher for p-polarized light, we also observe a deeper crater when p-polarized light excitation is used. Now, when it comes to the diameter uh, of the ablation crater, we determine them with as a function of your polarization and angle of incidence. And as we know, when we do ablation at oblique angle of incidence, the beam spot will have a shorter axis and a longer axis. So basically, the diameter will be different for the short axis and on the long axis. However, we see that the size of the ablation crater, meaning the diameter, will increase with the laser energy pulse. And since the temperature decreases with the increase in angle of incidence, the resulting diameter will also change. However, again, when we use p-polarized light, we can obtain a bigger uh, ablation crater compared to the S-polarized light. So the result of our investigation here show that the angle of incidence will be an important parameter when we do uh, pulse laser ablation at oblique angle of incidence along with the polarization. This will be important in some optoelectronic applications, especially if you want to do some more complicated surface patterns for different applications such as sensing. Uh, the material property, which is the energy needed to initiate the ablation, is also determined. Uh, what we have observed is it will be easier to do ablation for p-polarized light excitation compared to s-polarized light excitation, uh, which is an important uh, conclusion if we have to do some experiments such as pulse laser deposition. That will mean that the uh, polarization of the excitation has to be properly oriented in order to improve the deposition or the ablation efficiency. Now, allow me to move on with the deposition part. So this is a natural consequence of the pulse laser ablation. So since in pulse laser ablation, we have a material removal scheme. In the pulse laser deposition, we put a substrate opposite to the target surface so that the ablated material will recondense on the surface of the substrate to create thin films. Now, in the literature, the post-laser deposition is usually done with different pulse lasers such as excimer lasers and Nd:YAG laser. However, in the late 80s, the technology of femtosecond pulse laser improved, and that enabled the use of femtosecond pulse laser in the deposition. Now, in the presentation today, I will focus on the two recent publication of our group in PLD. The first one uses nanosecond PLD. This one uses Nd:YAG laser to do ablation, and on the Other one, we use femtosecond pulse laser in the deposition. Let me focus first on the nanosecond PLD. So in this work, we are able to produce iron oxide nanowires using pulse laser deposition. But the production of the nanowire from PLD, straight from PLD, is quite complicated or rather challenging. That's why we have to do what we call carbothermal oxidation of the iron oxide deposit. So in the first part, we deposited iron microsphere in the surface of silicon using Nd:YAG pulse laser. And after we obtained this iron microsphere, we placed them in a carbothermal oxidation chamber. We placed activated carbon at the bottom and heat up the system at different temperatures up to 800 degrees Celsius. So these are some scanning electron micrographs of the synthesized iron microsphere on top of the silicon substrate after the nanosecond PLD. So we can readily see that there's a presence of a microsphere on the surface, and they tend to be bigger when we increase the deposition time, which is proportional to the number of laser pulses. Now, after obtaining the iron microsphere, we place them in the carbothermal oxidation chamber, and the result is we are able to produce iron oxide nanowires as large as 10 should be micron, 10 micron diameter. The nanowires are on top of the surface of the iron microsphere before. Okay, aside from the nanowires, we can see some nanopores and these nanoflakes. Okay, now these are some side view of the microsphere just to check the length of the nanowire produced, and the FTIR and the EDS confirm the presence of the iron oxide on top of the iron microsphere. The thermodynamics and the kinetics of the production of the iron oxide from the iron is quite interesting because we think that the presence of Fe3O4 as a metastable phase is needed in order for the iron oxide nanowire to grow. So the tendency is for this metastable layer to initially form on the surface of the iron oxide, on the iron microsphere, and the iron will diffuse from the microsphere towards the surface, producing iron oxide nanowire. So that ends our work with the nanosecond PLD. Now, this nanosecond PLD, as we have observed in the previous work, produces micron-sized structures on top of the substrate. Now, it turns out that when we use femtosecond laser pulse, we can observe larger amounts of smaller deposits, and some of them is nano has a size in the nanometer range. So what we did is we used the femtosecond titanium sapphire laser. That's a femtosecond pulse laser to do the deposition. And in this case, we used Nd:YAG laser crystal as our target for the deposition. So this is the X-ray diffraction patterns, and we see that the produced film has a preferred orientation in this direction, and the structure can be improved by application of the heat treatment. So this is the surface topography of the as deposited film, and we can see that the variation in height is within few tens of nanometers, which indicates the production of nanoparticles. Now we applied two different heat treatment. The first one is the in situ heat treatment, and the other one is the post-deposition heat treatment. Just to check, just to check its effect on the topography of the deposited film. So we can see that the both heat treatments tend to decrease the size of the deposited particle with the increase in temperature, and more islands can be found at post-deposition heat treatment. In order to explain this result, we applied, or rather we used the thermodynamics approach in describing deformation of the thin film. So we have here the volume free energy of the system as a function of your pressure and temperature. Essentially, when this volume free energy decreases, the three-dimensional island growth is preferred. And when we increase this volume free energy, the two-dimensional monolayer growth will dominate. Now, to compare the two heat treatments, we parameterize the pressure as a function of your alpha and beta. Now, in the in situ heat treatment, we are applying heat treatment while we deposit the film. But when we do the post-deposition heat treatment, we have a two-step process. We first deposit the film, and then we apply the heat treatment. This differences in the application of temperature uh, changes the overall behavior of the volume free energy. That's why we are able to see more island growth in the post-deposition heat treatment, mainly because the decrease in the free energy is greater compared to the in situ heat treatment. We also tried to do parametric investigation using different background gases. So for example, we have a nitrogen background gas. And when we increase the nitrogen background gas pressure, the tendency for the particle is to uh, coalesce with one another. And we explain it again using the volume-free energy. Okay, but when we use oxygen background gas, we did not observe the same behavior, and we think it's because of the chemical interaction of the oxygen with the Nd:YAG laser as it is being deposited. This is the reflectivity, just to measure the optical band gap of the deposited film, which is quite close to the expected band gap of the Nd:YAG laser crystal. Now, before I end my presentation, allow me to share to you some of the current activities of our group. First is we are now working to extend our work to non-metallic materials. For our first move is towards semiconductor material. And since this is a different material, we can expect different physics of ablation. In fact, for metallic material, it is often enough for us to describe it in terms of the temperature. But when it comes to semiconductor, we have to take into consideration the carrier generation. And this work is currently being done by our colleague, Joseph. But what's interesting when we talk about semiconductor material is the cases where there might be an ablation but it is not thermal in nature. As long as we pass what we call the critical current density, the ablation can occur. And this is the case when we use multipulse in our uh, simulation. We can see the incubation effect, that the higher the number of pulses, we can accumulate the temperature and the carrier density. On the transfer mechanism from the ablation to the deposition part, this is currently done by our colleague, Romil Emperado. But the point of this investigation is to investigate the dynamics of transfer from the ablation to the deposition part. And as we can see, this part will play an important role in the deposition because of the physics and chemistry of the transfer of material from the target towards the substrate. For example, what will happen if we put a physical mask on the path between the target and on the substrate? Essentially, a majority of the deposited material will be placed opposite the mask, and we can expect some movement of ablated particles from the side of the mask. On the last part, we are interested in further improving the temperature model. And in this case, we are curious what will happen if we modify the laser source term. In all of the computational researches done in modeling ablation of metal, they always assume a Gaussian intensity profile of the laser source term. Now, what will happen if it's not Gaussian in nature? So we have a Lorentzian and hyperbolic secant beam profile, and as expected, they look like Gaussian. However, we think that the differences in the uh, profile of the intensity will manifest itself if we have larger amount of pulses in the ablation part. And on the other hand, experimentally, it's not perfect Gaussian. It's not always perfect Gaussian. So what we did is to do some multi-term Gaussian fitting in the laser spectra. And we observed that aside from the main pulse, we have some side band. What we have here is a pre-pulse and post-pulse distribution. This is important because in many experimental works, people will try to explain it by assuming that there's a single dominating pulse on their calculation. But in reality, there are some energy before the main pulse and after the main pulse. And this energy will drastically change uh, the energy distribution on top of on the ablation part. Before I end my presentation, I'd like to thank the Natural Science Research Institute, the UP system for the Enhanced Creative Work Research Grant, NRCP, and for the thesis and dissertation grant of the OVCRD of UP Diliman. With that, I'd like to end my presentation. Thank you very much.
All right. So thank you, Lian. So we have time for one or two questions from the panel. Anybody?
Sure.
Hello, Ate Bani.
Hi,
Sir
Lian. Nice
Balowi.
to see
Okay.
you. I
Nice
have
to
a
see you too.
question about the angle of incidence of the laser.
Yes,
And
ma'am.
does this affect the quality of the surface quality of the deposited material on your substrate?
When we're talking about the angle of incidence dependence on PLD,
Mm-hmm.
uh, we did not do a systematic investigation on that. But
Mm-hmm.
when it comes to ablation, uh, there is definite changes in the surface morphology and topography of the target, but not on the target. The question on its effect on the film is still an open question. But thank
Okay.
you for the research idea.
All right.
Good luck.
So
Thank you very much.
we have another question from Dr. Hermosa.
Hello,
Hi.
sir.
Hello, Lian. Thank you very much for the for the presentation. Um, okay, I have two questions.
Yes,
Maybe it
sir.
will have three. It will be three or four. But the first question is it intuitive? Because what you did is to look at the ablation, different angles for a particular metal. Is that correct? A particular
Yes,
metal.
sir.
um, Intuitively you have a more absorption for a certain angle with depolarized light.
Yes, sir.
Well, does it correlate nicely, or there is some factor to it?
Uh, some Japanese group did a systematic experimental investigation on the dependence of the crater to the angle of incidence and polarization. And they conclude that it's more efficient to use p-polarized light, and they attribute it uh, to the
Yes, yes, yes.
resonant absorption of the laser energy on the target. So in terms of correlation, perhaps I pwede ko sabihin, I can say that it has been observed experimentally.
So in relation to that, um, for semiconductors,
Yes, sir.
you can it also has some if you look at the displacement, the d, it's just one proportional to 1 over also a resonant frequency, right? um in the Drude model, uh, wouldn't you have the same results for metal and semiconductor?
That's a good question. Uh, right now, I would say it's an open question. The good thing is it can be done easily. I believe Joseph has a working code now, and I have a simple modification on the laser source term. So the safest answer that I can say is please wait for the result of the
All
computation.
right.
But it can be easily done, sir.
Okay, thank you very much.
Thank you. Thank you, Dr. Hermosa, and thank you, Lian, for the
Thank you, sir.
presentation.